init, string, and print car with our documentation that we've added to those. Good deal. So let's create another object. I'll call it NS2, and this time let's supply 2004 Honda Element. And of course I ran into a glitch here because I didn't use the full namespace, did I? If we were using from classes import car, that would have worked. But we just imported all of the names, which maintains the existing namespace of the classes module. So I have to prepend classes to car to get this to work. If I run a type on the NS2 object, it tells us that this is a class, and it gives us the object name of that class. Classes.car is the parent class here. Now, if we did a str on NS2, we get back our custom handler. We can fetch any attribute we want here just by supplying the proper namespace. We can do an ns2.year to get back the year, ns2.make to retrieve the value of that property, ns2.model is element. Now what if we wanted to make a change here? Can we override inherited values? You know we can. How's that? ns2.year equals 2010. And you notice that we get back an updated value there by making that change. What about ns2.static? No problem. Let's run print car. ns2 dot any IDE worth its salt is going to give us a list of the attributes and methods that are available. You see print car is in that list, and it runs the function with the update that we overrode from the parent class. Let's talk a little bit more about these Python special methods or magic methods that we can include in our class definition to customize the behavior of instances. We already saw how we can use _str, to manage string conversions. We also have REPR that does the same thing. Generally speaking, the REPR gives a more accurate string representation than str. However, str tends to be the more popular way to do string conversions. Another popular special method you'll see are the mathematic-oriented ones. In other words, what happens if you create two instances and perform addition, multiplication, modulo division, straight integer division, etc.? Well, you can provide function definitions that modify that behavior using these magic methods. Add for addition, sub for subtraction. Before I show you the sample code, let's go out onto the web one more time and look at the Python reference manual. You can get to this, as you know, through docs.python.org. We're looking at the 2.52 reference manual, but the same thing exists in the version 3 one as well. But the article you're looking for is called Special Method Names. It's really nicely specified here: basic customization, customizing, attribute access, and it gives you a detailed run of the syntax behind all of those magic methods. To finish this slide, let's look at a sample class declaration here. We're creating a class called bar, foo bar, spam eggs, the whole deal. And also, as expected, we have our constructor definition that involves just one formal input parameter, and we're setting self.a equal to a. In other words, just to create an object of that argument. To handle addition, we can add a method using add that involves another argument, in this case b. And in this add method, we're defining yet another name and returning that name out of the function called s that simply performs addition of the representation of a, self.a, and also, check this out, this can be a little confusing at first. We're taking b, the second addend, and we're applying the a property to it. So in other words, we'd wind up with b there. b.a is equal to b. And then, as I said, we're returning that value. So in our code, we could create, say, a name called x, where we invoke an instance of bar with a value of 10, a name called y that creates an instance of bar with 20, third name that takes x plus y. That works okay because of this add magic method handler. And then if we print the value of z, we get 30. Pretty straightforward. Works the same way for all of the other mathematic-related handlers. In this final demonstration, I want to show you how to subclass. The reason why we'd subclass, of course, is to take advantage of the encapsulated attributes and methods in a base class and reuse those through inheritance. So we have our car object, and that gives us make, model, year, etc. Does some pretty basic stuff. Let's say we also want to create a class or another object to embrace motorcycles instead of traditional four-wheeled vehicles, which are embraced with car, let's say. Well, we could either create this motorcycle class and inherit from object and recreate all this stuff, or very simply, we can subclass motorcycle and inherit from car. And how you do that, as you already know, is to use the class statement we provide the name of the class, and then the parent class from which we're inheriting. You also know that we can use pass as a way to just kind of put on ice that function, method, or class definition, and we can do code with it later. Pass is useful in our case today because all we're going to need are year, make, model, and static, which come to us through inheritance anyway. You see what I mean? From the interpreter, we're not going to run the from import type. We're actually going to import everything from the class's library that we've done. And let's create a name called MC. That's an instance of the motorcycle class. Because motorcycle inherits from the car class, we're going to need our 3 parameters, aren't we? So let's do 2008 Honda Shadow. And again, we run into the name qualification issue. You probably saw that before I did, didn't you? Gives us good practice, though. If we invoke the dot notation and pause for a moment to let the Python shell or the idle IDE give us our methods, notice that we can access make, model, year, we can pull static, as well as the print car function. In other words, we've inherited everything from the parent class. MC.static, and just as we saw before, no big surprise, we can redefine any of this stuff to our heart's content. Simple as that. Object-oriented programming review. In this nugget, we formally defined object-oriented programming and compared it to the procedural paradigm that we've used for most of the course thus far. At this point, I hope you're familiar with what a class is, how inheritance and encapsulation work, how we can subclass an existing class, instantiate instances of a class, etc. The whole deal. As I told you at the beginning of this nugget, we'll be able to get some more practice with OOP principles in the following nugget, in which we cover GUI, or Graphical User Interface Development. I hope that this has been informative for you, and I'd like to thank you for viewing.